but then it's a trade-off, because if you do this kind of access pattern, you are very good for the coalescence, so that's great, but your cache access may be a bit poorer. So depending on the cases, you want to sometimes maximize locality and sometimes coalescence. And if you can both, but that's not always possible. We will get to that. So that was for the summary. So if you want to go fast on a GPU, there is a big question, which is what kind of reals should you use? Typical consumer GPUs are really good at floating point performance. You see here 30 teraflops for an RTX 3080, that's huge, but really, really poor at double performance. And although that's not really as bad for data centers GPUs like the A100 on the Lucia cluster, there's still a difference in general. And even, for example, on Lumi, where the two are theoretically the same, they have 47 teraflops of both FP32 and 64, you still pay the price of the bandwidth. So if you can, you should try to use floats, but sometimes you can't. Here you see an example of, I mean, this is going to be what you do. This is going to be the result of the exercise. And when we first did that, when I was doing my master's thesis, actually, that I don't know if you can see here, but it's a bit blurry. It's not really good. And that's because with floating point, there was a big difference of two close numbers at some point. So we lost a lot of precision there. And we were able to change the formulation so that it works. So now we get this even with floating point with floats. But it's not always possible. So tip one, if you can, use floats. Tip two, so here is kind of an example of what we would have on a CPU code. You don't care about the details. Essentially, we have a part where we load a bunch of data, then we do some heavy processing, then we store the result back to the CPU, to the memory, sorry. And so if you come from 10 years of doing something like this, you're going to say, okay, I'm going to need to optimize the computation because the computation is where all of the time is spent, etc. But then you port it to GPU, and when you benchmark it, well, this is not really the bottleneck anymore. This is only 30% of the time. And this is the reason why a lot of this talk is going to talk about the memory access pattern and the memory in general. It's because GPUs are really good at doing a lot of floating point operations, but the memory is comparatively much slower, and also its latency is really high. So in general, memory operations are the bottleneck. So here's a typical example of where memory is a bottleneck and how we can improve it. And this is one of the things that you will do in the exercise. So the idea here is that we have a finite element code. And so each triangle is going to update its value, and to update its values, it has to get the data from itself and from its neighbors. So if we have a mesh ordered like this, so I don't know if you can see, but there is a continuous line which goes from one element to the other, and that represents the order of the mesh. What you'll get is an access like this. So first, we load the data for element 42. So it's located in this cache line. It goes into the cache. Okay, it fills part of the cache. Nothing that we can do about it. Then we load data from element 12. Again, we fill the cache. Nothing better can be done. But then what's a bit sad is that when we load the data from this element, the cache is full. So we have to kick data from the cache. And so we can't reuse the data for element 42. And same story here, we have to kick stuff from the cache. And that's a bit wasteful, because in an ideal world, all of these data should be close together in memory so that they are on the same cache line. So ideally, we would like an access pattern like that. And it's actually possible to do that even with an unstructured mesh by reordering the mesh here along a Hilbert curve. And you see that when you do these kind of things, you dramatically increase the chances that elements that are close together in space are also going to be close together in memory. So you have this kind of access pattern. Sometimes you're going to have a cache line, a neighbor that's completely in the other, in another region of the memory, but that's okay because it's fairly rare. So that's how one way to improve the locality. And now a question becomes when do we need to do that? When do we know that actually our code is using way too much memory? Because remember in this example here, this loads data from global memory, this loads data from global memory, these two and these two. So we're going to load 4 times too much data. And when you use the inside profiler, what's going to be typically, it's going to look like is typically something like this, where here I read 1 gigabyte, but only write 70 megabytes. And I know because I wrote the code that it's not normal. You should have a factor of, okay, perhaps 2, 3, 4 here, but not like 10, 15. And also, the profiler is really good because it is going to yell at you if you do this kind of access pattern. So let me DRAM excessive read sectors. It's really small, but it's telling you that for all the sectors that you read, you are only using, let's say, 1 element over of 10, I don't know. Okay, so that's the second tip. Try to maximize locality when possible. So is that the conclusion? Should we maximize locality? And again, no, not always. Here you see an example of a code that just sums up a bunch of different pieces of data. So in this case, one thread just reads contiguously in memory. In this case, one thread reads at one point in memory, then much further, etc. You have to think of that as a C-style memory layout. And what we can see, surprise, surprise, well, not really. The really local access is slower than the other one, and because this one is coalescent. Do we have next slide? Yeah. It's basically this picture again. The local access does this, but since all of the data does not fit in the cache, well, bummer, we are going to read multiple times from global memory, where in this case, we just read once. Again, we are hammering on this, but it's one of the main differences with a CPU. So trying to optimize for coalescence is also a good idea in general. And how do we know if we have to optimize for coalescence? Again, image from the profiler. The profiler is going to yell at you if your access is not coalescent enough for its liking. So here it says memory access pattern for global blah, blah, blah. Where is it? I'm not finding the word that I wanted, but it mentions that it's not coalescent. Yeah, okay. Check the source control section for uncoalescent loads and try to minimize well them. Okay. Tip number 4. Can someone tell me what's wrong in this code? Any idea? It's really subtle. There is one problem with this code. No? The problem is this. Again, here we do 1.0 divided by the determinant, and here 1.0f. What's the difference? Well, 1.0f is a literal for a floating point value. So float divided by float is a float operation. However, if we do this, this is a double value. This is in the float, is a float value. So you have double divided by float. The rules say that the float is promoted to a double, and so you have double divided by double, and you do a double operation. Again, on GPUs, yeah? In this case? Yeah, because no, here. Because you write floats, you need to pass. Yeah. Yes, it's cast to, yeah, you are correct. The compiler casts it back to a float. But the multiplication is done in double precision anyway. Okay. I think that what one could make an argument that if the result is cast back to a float, you do the floating point multiplication. No, it doesn't tell you anything. This is a really silent error, and it's really subtle. You have to know that it exists in order to try to find it. And perhaps if you do fast math, then he doesn't care, but I didn't test that with fast math specifically. So yeah, be aware of double literals. And if you have a code that can be compiled either for double or for floats, maybe you don't want to do 1.0f because, I mean, 1.0 is not a good example, but if you have pi, you don't want to use pi as a floating point value. You want the full fat pi when you compile with doubles. And so you can do user-defined literals or explicitly cast to your scalar type. I mean, solutions exist. And how do you know that you are doing double operations? Well, two ideas, two cues. Here you have the roofline chart at the top of the profiler, the NCU profiler, and you see two dots. So did you explain how to read this chart, or should I say? Okay. Okay. So let me take some time to explain what this is. So this is a chart which plots the amount of flops that we do, so the amount of computations, versus the amount of data that we use vertically. So a dot is going to be what our kernel did on average as a summary. And so a dot that's here on the right means that we do a lot of computation. Here on the left, we do very few computations. Above means that we do a lot of memory operations, and below, very few memory operations. So that's what the dots mean. Then there are those lines. And what those lines mean, well, this line here, this diagonal line, is the roof line for the bandwidth. That means that how can I explain that? If you use the full bandwidth of your GPU, you are going to be somewhere on that line. If you use if, for example, for each byte that you load, you do one floating point operation, you are going to be located here. And if you are able to load data at the maximum speed of the GPU, well, you are going to be on this line, this roof line for the bandwidth. And you see that the more the compute intensity you have, so the more the more flops you do per byte that you load, the higher the line is, because the line plots the memory per operation. Anyway, the key thing to understand here is that when you are against this diagonal line, you are bandwidth limited, and on the opposite, these horizontal lines are the compute limited lines. So there are two of them because doubles and float. So this is the line for double precision, and this is line for single precision. And if at some point your kernel does too much math, even if it uses very, very little amount of data compared to the math that it does, so we're going to be around here. At some point, you are not going to be able to get higher than these lines because you still need to do the computations. So this indicates the bottleneck, the bound on the amount of computations that you can do. So a kernel that is 100% efficient on the computing side of things, so that a kernel that does 100% of the arithmetic computes, that stresses the GPU to the maximum with the floating point arithmetic is going to be on one of these lines. This for doubles and this for floats. And so here you see two dots. Well, why two dots? So this plots the floating point compute intensity for 32-bit floats, and this is for 64-bit floats. So doubles and floats. My point being, if you have two dots on this chart, it means that you are doing double operations, because here you have the dot for doubles, here you have the dot for floats. If you don't do any double operations, you don't have that second dot. Okay? And so clue that you are doing the double operations, well, you have that second dot. Now, if you are lost in your code and you wonder, okay, I know that I'm doing a double operation, but where is it? I don't know. There is this source tab on the profiler. And on the source tab, you can see your source, and you can also see the generated instructions. And you don't need to understand any of that, except that if you do a double operation, it's typically going to be a DMUL or DFMA. So if you look for DFMA, okay, here I see a DFMA, and then when I click on that, it highlights the corresponding part of the code, so you can find where it is. And that's a really useful feature sometimes, especially when the code is big. Okay, then another tricky one. At some point in the development of my code, I removed the printf because it was not used and I didn't care. And it made the code 1.2 times faster. The printf was never reached. It was never accessed. So what did happen there? So I changed the code to this, and suddenly it's faster. Well, the problem is that on the GPU, on each compute unit, you have a limited amount of resources. So if your kernel uses a lot of registers, you are not going to be able to put many wraps into the compute unit. But if your kernel is really light, then you can put more wraps in the compute unit, and so you have a better what we call occupancy. And what happened here is that if this is the total amount of resources of registers that I have on my compute unit, that was my kernel. We can fit 2 wraps. And removing this tiny bit of code allowed me to put a 3rd wrap. So that's the kind of thing that happens. Take away from this, if you have code that you know is not going to be executed, do not put it. It may slow things down. It may also very well do nothing, because there were cases when I was trying to recreate this case, actually, and it didn't work because we were in a situation where the 2 wraps take this amount of space, so reducing them a little bit still allows me to only put 2 wraps, so it doesn't change anything. Okay, and so when is it interesting to reduce the amount of registers that we use, so reduce the number of variables in the kernel and the instructions? Well, in generally, it's almost always, but it's going to be especially interesting when you are on one of these steps here. So what's this? This is a chart, again, from the profiler that shows you how many wraps can you put on a compute unit, depending on the number of registers that you use. If you use many registers, you can put one number. If you use very few registers, the number is higher. Anyway. And what happens is that when you are here, a bit to the right of the step, and you reduce a tiny bit the amount of registers that you use, well, you can increase the number of wraps that you can put on a compute unit, and that typically translates to performance gains. Okay. So the way I planned things was that, so these are the first 5 IDs, and now my suggestion would be that you start the exercise for a bit. So the 5 points that I presented is literally the 5 first exercise. And then there's going to be a second part, and we can perhaps do a small break in between, if that's okay with everybody. Okay. Do you have access to either NVIDIA GPU or the cluster? Hmm? Hmm.
So everyone who requested to get access to Lucia got access to Lucia?
Yep.
I received the passport, and then when I want to connect myself, there is like a connection confused, and then there's a number error, like 65.
So the password is meant for the web interface, not for SSH access.
No, but like we see the mail from the Lucia, from the scenario, and there was a passport, like they gave me a passport that I have to change myself.
Yeah, for the web interface. So if you read the email correctly, they say that to access you need to use your CC account with the CC key and configure it like other customers.
So actually, I received the same message when I connect to the mail from.
Okay, if you, oh no, I'm not sharing my screen anymore. Okay, did this work? Yes, it did. The exercises are on this repo. I'm gonna copy them to the folder on Lucia. So it's perhaps interesting to say something about those exercises. Wait, let me put them. Do I have it here? No, I don't. Anyway. Pour la captation, c'est chiant si je me déconnecte maintenant ou Ok. Je vais passer sous Linux parce que ça m'emmerde. Wait, why can't I restart? Come on. Who doesn't speak French here? Okay. Yeah. Better in English, I guess. Lucien, on peut se connecter avec VS Code ou ils sont pas chauds qu'on fasse ça? Je sais pas. Je sais que Lumi, ils l'ont interdit. Ah. Je vais remettre ça à l'écran. C'est Miguel DLC / ceci GPU. Et je voulais les copier. Non, c'est pas ça que je voulais faire. Je voulais les copier dans le dossier du truc partagé, mais j'ai pas encore fait. Okay. Okay, I also put the exercises here on Lucia. And now, no, super. Perhaps I should explain how this is structured. So you have you have 10 folders here from 1 to 10, and the idea is that it starts with a code that's it's a finite element code that simulates an ocean anyway. It doesn't really matter, and the solution to the first exercise is the statement for the second exercise. The solution for the second is the statement for the third, etc. Until the 10th, which is not an exercise. So this is the final result. And so the way it's done is, okay, let's go to first one, for example. If you have an empty folder, you don't have the slum.out. This is because it's my tests. You don't have solution. You have main.cu, main.h, make file, plots, and that's it. You can run make to compile things. actually, you're going to need to load an environment. I should have put that somewhere. And then if you want to run the codes, you have two options. You can either do an salloc to get a dynamic session, or if you don't want to bother with that, where's my mouse? Here it is. No? Okay. You can see batch the run.sh. And it's gonna run.
Okay, can I add something here?
Yeah.
So there is a account on Lucia for this session. So if you use sbatch, you need to use -- account ccgpu. So the same name as otherwise it will be accounted on your other account. That's the first thing. And the second thing is that there is a reservation on 2 nodes. So it's 8 GPUs in total. But if you are part of the project, you can access the reservation without any addition to your submission script. But it means that if you do salloc and then just sit on the GPU for the whole time, you will prevent others from accessing. So it's better to use sbatch and submit your job and then see the results in the file.
And
you said that when using it as a batch, you need to send the account.
It's on there.
Okay, sorry, I didn't see.
Yeah.
If you put it twice, it will be twice as fast.
Yeah. If you have trouble compiling things, you can load those modules, especially UCX CUDA, which includes the compilers and everything. And please do not hesitate to ask questions. I know it's a bit rough, and since it's the first exercise session, I don't know if the difficulty is going to be all right, extremely simple, or way too complicated. So please interact. Yeah.
Before running like as batch code,
yeah.
So we need to compile it.
Yes. First do a make. No, ideally you should probably copy that to your home or somewhere like that.
If you clone
if you clone the repo, you're good.
Okay.
If you clone the repo, you're good. The only difference is that here I have a bigger data file in the data folder. Yeah. Yeah. I tried yesterday with those modules and apparently worked. Let's try again. Yeah, okay. And when you do a batch here, it's gonna run the script once, which is gonna print. Well, actually, I can show you the results. So the result should be something like that. Have the time per iteration, and also an NCU file for the profiler.
I don't know if you can read that from there. I guess not. Can you read that? No. I will rewrite it here. It's typically the issue that only one side. I'm not sure if this if that one is capital or not. C'est pas capital?
Non. Le P de paille.
Le savais pas?
Ouais. C'est une saleté, mais là, il est dans ma tête.
Je suis autocomplétion, donc évidemment.
Tu laisses batch ou tu laisses...
C'est bien.
C'est dans le train, là?
Oui.
Bon, bah alors ça génère pas la figure. C'est pas très grave. Hein. En théorie, ça génère une figure qui est le résultat sur des séries. Probablement, mais vu que ça marchait avec ça, je ne sais pas te dire. Attends, sinon je peux regarder. Question? Yeah, it's the same error. I'm going to see why it worked yesterday and not anymore. Oh, perhaps you can just do pip install matplotlib after loading Python.
Okay.
I think that should solve it.
Ouais, si on est sur le même. On est sur des sessions différentes ou pas?
Non, tu es de copier ça avec les temps. Non, tu copies ça dans ton home sur le serveur. Oui.
Is there anybody else who does not have access to the CCTV project even though they requested it? No?
C'est la validation.
les jours. Ce qui est un peu dans
En ligne de commande, c'est compliqué. Donc, soit tu la copies de fait chez toi, soit en se connectant à SSH via le studio code, il y a moyen aussi.
Alors, sur mon ordi?
Ouais.
Ok.
Tu peux voir des images comme ça.
Non, non, non,
J'avais testé le module Python qui permet d'écrire une image en ligne de commande avec des caractères colorés. Tout ça. J'ai abandonné. Non, c'est pas dans ces GPU, il y a des images. A4, c'est 6 GPU, c'est 6 GPU. Non, GPFS, projet A4. Joli.
Ça fait gagner parfois une demi-seconde.
Avec 2 secondes, GPU, c'est beaucoup. Hein.
Ah, Nicolas, c'est un peu tard. C'est un peu tard dans son projet maintenant.
C'est grave, c'est grave.
Moi, je viens de recevoir la lettre que tu t'es mis dans le projet, mais ce sera demain que ce sera cliqué sur l'initial.
Oui, j'ai vu.
Qui ça? Il y a deux frontales et tu passes de l'un à l'autre. Dans le premier mail initial, ils te disent ce qu'il faut mettre dans le post pour ne pas avoir le problème. C'est évident.
Ok, ouais.
Je peux pas te le partir, c'est tout à
Ouais,
fait.
ça.
En fait, il y a plusieurs clés qui communiquent. Ce sont plus celles-là.
Pour prendre un peu la température, est-ce que vous avez pu faire tourner le premier, voir un peu ce que ça donnait, puis peut-être le deuxième, ou faire les changements, ou pas encore?
L'exercice qu'on doit regarder pour vérifier que la différence c'est bien le time.
Oui, ça c'est une bonne métrique. This is a good metric.
Le temps, sinon, c'est normal qu'il fluctue un peu.
Mhm. Et si tu veux une bonne indication de ce que tu peux avoir en faisant la modification prévue, ben, il suffit de run l'énoncé suivant. So for these exercises, all of the modifications are in the header file, main.h. And you should see a big comment saying modification starts here or something like that. So here's the example for the first exercise. And okay, I'm going to give you the solution. It's to type def the scalar as float and not as double. And just doing that is twice faster. The code is made such that the changes are really minimal. But I still encourage you to run it before, look at the profile result, and run it after, and look at the profile result. You need to install NCU, so CUDA tools. Windows? Ubuntu? Probablement CUDA tools. Ouais, mais c'est gros. Yep. I wrote the whole program such that every time I define a variable, it's defined as a scalar and not as float or double. So if you change it here, you change it everywhere. In practice, you would need to change it everywhere. Voir si je peux faire un petit peu de correction pour les premiers exercices, comme ça on avance. Ouais. Is it running? Can I do maybe a small comment on the first exercise and continue?
How long is it supposed to run?
About 2 minutes. Half of which is generating the plot. Pim pum pum. Okay, small comments on the first exercises. Okay, these work. Since apparently many of you do not have roots NCU, I'm showing it here. So this is what you see when you do the profile of the first exercise without any modification. So what's interesting is to look at the roofline analysis. So it's, oops, where is it? This chart. And as you can see, we are pretty close to the bandwidth limit, which is this tilted line. And here you see the single precision compute. So we do a bit of single precision arithmetic and a lot of double precision arithmetic. And how much exactly? Boom, boom, boom. Is it here? No, it's a bit. It's hard to read backwards. Okay, Kernel achieved 1% of the device FP32 and 32% of FP64. So the Q here is, okay, 30% of FP64 is a lot of FP64. What if we change that to float? Can that be better? And when you do that, bim, bam, boom. That's after the modification. You see this. It looks very similar, except that it's the opposite. This is the FP32, and this is the FP64. So we still have a bit of FP64. We'll deal with that later. But now the FP32 is much higher. And the code is also, I think, twice faster. So here it says 700 microseconds, and here 1.13 milliseconds. So it's an improvement. All right. And what's interesting to look at here is this part, the memory workload analysis, where you see a bunch of warning signs. And so that's going to be telling that, well, you do a lot of memory transfers, so perhaps you should try to optimize that. And to do that, there are two mesh files, one which is the original mesh file, which is completely random, and one which has been sorted. So it's just a matter of swapping and looking at the results. Il y a deux choses, il y a les instructions et les datas. Typiquement, ce qu'on data, c'est les datas. Donc, plus il y a de variables, plus ça prend de la place. Typiquement, une variable va être stockée sur un registre, un float, un registre. Et donc, si tu as 40 floats, ça prend 40. Ouais, je pense que c'est ça, plus quelques instructions en plus, qui font que ça prend du temps. Et d'ailleurs, je vais vous montrer le résultat, mais on voit clairement le nombre de registres passe de 90 à 70, un truc comme ça. Hmm?
Is there a difference between using global or using closed events?
Yes.
So it's not something.
Yes, global in the case of the what you are writing is a kernel. So it's the kernel is a function that can be launched on the GPU from the CPU. And when you use a host, it means that is a function that's compiled for the GPU. It cannot be, I mean, you cannot call a host function, but a kernel can call a host function. It's a function that can be called by kernel. And no, sorry, that's device. And host is, yeah, basically.
If you define host space device, and then something that's
it's going to be compiled 2 times, once for the CPU, once for the GPU. No, because inside of a kernel, you cannot call a global function. Oh, inside of global function, you cannot call a global function. On reprend la température, vous en êtes à où? Ok. Le 3, c'est... Ah oui, Coalescent. Ouais, je vais faire un petit mot. Small comment on the second exercise. It's also a really easy one, once you know what you have to do. What we had before, starting the second exercise, on the memory side of things, is all of these warnings, and especially DRAM excessive read sectors, which indicates that we have a bad access pattern, and which is shown here because we load 1 GB from global memory, and I know that we don't need that much. You don't know that, but I'm telling you, we don't need to load that much data. And so the solution is to change the mesh file from the GMSH one to the not GMSH one, which has been reordered. And when you do that, first things first, from 754 microseconds down to 434. So that's nice. That's a nice speed up. Also, you'll notice that before these dots were quite to the left, whereas now they are a bit further to the right. Where? Oops, no, not this way.
That's one thing I like.
Attends, je vais mettre ça ici.
Add baselines on the, and then you can go on the other one.
Uh-huh.
So click here, I guess.
I touch it.
Ah, you do it into okay.
Is what
it
doesn't
you see now you have all of them in the same place.
Well, perhaps it would have been better to do that on the side.
You can see your improvement factor.
Yeah. All right. Oh, that's right. So yeah, we increased a little bit the 64 and 32-bit compute amount, and we went from a gigabyte of memory read to 270 megabytes. So that's also a big improvement, hence why it's faster. For the next exercise, if you are a bit stuck and wondering how to do it, the idea is to have a coalescent access. What's a coalescent access? Is when consecutive threads access consecutive positions in memory. So Where is it? Let me take the exercise. Here it is. Where am I? Oh, no, it's not the last version. Anyway, it's this line that you want to change. And how do you want to change it? The idea is that this represents the data for a 3D array, so 3 dimensions, the node, which has size 3, the number of fields, which has size n fields, and the number of elements. And in this case, we have 1 thread per element. So you want that if I call this function with the same arguments and 2 elements that are consecutive, it returns 2 memory locations that are consecutive, meaning that the last index here on the right should be the element and not the field. That's basically what it means. Is that clear or is that blurry, I guess? And I know it's a tricky exercise, transposing a data layout in your mind and then writing it, then it's not gonna work and trying it again. Oops. What I meant to do.
Ici,
J'ai mis la solution. Ah non, attends. Ah non, c'est toi qui as fait ça. Okay. Non, c'est pas bon ça.
Ok.
Parce que tu as LM ici. Donc tu as LM là, c'est bien, mais du coup, tu fais pas.
NLM. Ah,
Ouais. Ouais, c'est ça. Ah. Non, il y a encore un peu comme ça. Du coup, c'est plus notre point. Non. Ça va être l'autre point. Ça, c'est des trucs. Il faut l'avoir fait 10 fois pour ça. Ouais, c'est ça. Ça, au lieu d'avoir un trait qui fait double, le trait suivant qui fait double, le trait d'après qui fait double, c'est avoir tous les trucs qui claquent, une claque. Juste un. Ouais. Parce que ce truc-là est appelé partout. Et là, si partout tu as des accès manuels, tu vas prendre ça. C'est pas parce que. Enfin, c'est pas toujours plus rapide. On mesure, alors on voit que c'est plus rapide. A quick word on the third exercise? Or do you want a bit more time? I don't think it's the most interesting one. It's important to understand what you do, but it's not important to understand exactly what the details are. And the conclusions are more important. So here's the solution. Boom, boom, boom. Where is it? So the important part is that the element, which is going to be one thread per element, so that's going to be basically the thread number is the last index. So consecutive thread, consecutive memory locations. And then the rest is just put there so that it does match. In this case, this layout is made such that we have the first field with node 1, node 2, node 3, then the second field, node 1, node 2, node 3, and inside of each node, you have the data for all of the elements. So this is the kind of memory layout that would make sense. And again, the only important part about this is that element is the last index. And we can profile that, we can benchmark that. After the modification. Come on. And you see it's a little bit faster, not by that much, it's a little bit faster. But here is an important comment, so pay attention. To do this exercise, I cheated. I did something bad because initially doing this modification was slower by 10 to 20%. So you may be puzzled, why would using a coalescent memory access be slower than basically a local and optimal? It's optimal for locality, the one that we had before, but why would that be better? It's because in this case, it's an unstructured mesh. So for each triangle, you have to access the neighbors, and the neighbors are not stored contiguously in memory. And so there is this lack of structure that makes locality really valuable compared to Coalescent. And that's why I had to cheat and modify the things a little bit to make this actually work. But the comment is still true. In general, it's good to have Coalescent accesses. But here, the price of locality was too great. So yeah, gonna have to find a new ID, which is conveniently the 7th point of the talk. And so what we did actually in doing that is that we can load less data because the way the data was structured before was something like this. This does not right. We had all of the data for element 0, then all of the data for element 1, and only this part of the data was used. So when we do local memory access, well, thread 0 is going to read this, thread 1 is going to read that. But so thread 0 is going to read the whole block, and thread 1 read the whole block. So we are going to load a bunch of unused data every time. And that's actually a pattern that comes very often when you do an array of structs instead of a struct of array. So it's not completely cheating. It's kind of cheating, but not completely. So yeah, that's the comment for this one. And what's the next one?
I have a question.
Yeah.
perhaps no. What if you add some like you have 4 instead of 3, so you have the kind of line you have there. I suppose that they are consecutive in memory, which means that the 4 elements actually first. So
I'm not sure I understand your question. Do you mean what if we had some padding here so that this is aligned and this is also aligned?
yeah, because in the memory you have it's aligned by power of 2.
Yeah.
And here you have 3 elements.
Yeah.
So you at some point on the cache line you must have
yeah.
something that is split.
Yep.
Which together. When you said it was slower, I think that and reading, but if I understood well, but you said it's actually not something else.
No, no. In this case, it's something else. What you suggest, I think, could work. If you have something like this, well, all of this is used. Then you have a bit of data that's not used, and the end of the cache line is, let's say, here. So you don't need to load that much more memory. Because when you load the cache line, you pay the price of the whole cache line. And you pay the price from global memory to the cache, then from the cache to the kernel, basically. And if you pack the structures densely, even if they are not aligned on the cache lines, so this is going to be your first cache line, for example, and this is going to be the second one. From global memory to the cache, you are going to read less cache lines, and that's where the impact is the highest. So you're going to win anyway. Do you understand what I mean or not?
Yeah, it's basically choosing the top, choose the one that is less.
Yeah. But when you do that, sure, blocks here overlap on different cache lines, but all of these cache lines are going to be loaded to the cache anyway. So once they are in the cache, it's faster. And loading data that's packed to the cache is going to be faster than data that's packed. Except, obviously, if the padding is relatively small. Exercise 4 and 5 are relatively fun, I think. So I'm gonna let you do them, and then we can move on. Vous en êtes où pour prendre un peu la température? Ok. Ouais. Non, si tu as N maintenant, tu dois avoir NN dans les deux. NN. Non, parce que du coup, NN, c'est pas ton indice, donc tu vas sauter le. Non, 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 non. Non, c'est genre 3, 8 et 2. Ah oui. Non, non, non. Quand il écrit pas besoin de changer, c'est ça. Le 4, c'est les prints ou c'est les. Ok. Non. Mais non, alors pour celui-là, c'est en gros, tu fais CTRL F, 1.0, 2.0, etc. 0.5. Et quand il écrit qu'une fonction est bonne, il pas besoin de la toucher, elle est bonne. Hmm. Vous pouvez parler. Hein. Attention. Ah non. Mhm.
En gros, La hauteur ici, c'est combien de thèmes? La combien de thèmes chaque thème? Et chaque variable, c'est ça, c'est pour il faut tout avec ça, c'est pas pour faire c'est pas donc en fait, c'est les descriptions ici instructions et probablement aussi les data pour stocker le prix. Okay.
Should I go ahead for a comment on exercise 4 and 5, or do you still want a bit of time? Who's okay for the comment? Okay, let's go. Where's the mouse? Where's the mouse? So we started with the result of exercise 3. And interesting thing to see here is that we still have 64-bit computing happening. We still have double arithmetic triggering. So we don't want that. That's due to float literals, so things like 2.0, etc. And simply removing that as a baseline. Okay, so this is 300 and something microseconds. Significant upgrade, 367 to 317. And, oops, no, too far. What we see here is that we still have this dot, which is the 32-bit floating point amount, but we don't have that dot anymore. That's the baseline from the previous kernel. And so as a result, it's faster, and you can see that this dot moved a little bit higher because we do a little bit more computations. And yeah. And again, this is from just changing a few numbers in the code. So it's really easy to do, and it does pay off because this is significant, it's measurable. And then the problem of the printfs. Yeah, here I want to show now this part. So as is almost always the case, our kernel, the occupancy of our kernel is limited by the number of registers used by the kernel. And how many registers do we use? Well, let's go to this little dot. And it tells us 96. So we use 96 registers per thread. And on kilo hardware, one register means one float. So one 32-bit value. And if we just remove there are two printf statements and an if statement that's never true because the problem is well done. again, significant improvement in performance, which can be explained by the number of registers that we use per thread, 72, down from 96. And 96 was here. So you see that we are one step further. So we can put more warps per compute unit and thus have a better occupancy. Okay, do you have questions regarding the first exercises or the topics covered so far? Should we move on to the second part? Okay. Oh, I'm not sure this is gonna work. Yeah, I'm gonna go back to Windows. Sorry. Let's seize the pause.
Has everyone signed the attendance sheet this morning?
Okay. It's coming. Does this work? Doesn't this go away? Nice. Okay. Let's continue. 4 more topics. No, it's not. Why is it not working again? Come on. Just say. Okay. Oh, I didn't plan my presentation. Okay, so next idea. With all of the optimizations that we did to the kernel, we went from a timeline where we spent like 95% of the time doing the computation in the function called dudt, and then the remaining 5% in the AXPy. So dudt computes the derivative, stores it in the buffer, and then we add the derivative to the solution, thus giving us the next time step. Simple temporal scheme, we don't care about it. But since we improved the dudt function very significantly, we now reach a point where the dudt function, it's actually very comparable to the AXPy, which simply adds the results. And so this can happen in a variety of different circumstances. And when you have that kind of thing where the next function uses the result of the previous function, it's sometimes a good idea to merge those functions, and that's what we call kernel fusion. So the idea here is going to be to just do everything in one function. You just need to add a few arguments to the dudt function, and you can completely bypass that AXPy. And you'll see in the exercises that this is very significant because I think we gain a third of the time, something like that, which roughly matches the size of this XPy compared to the DUT. Okay, so that's one idea. Other idea, using shared memory. I guess you were shared memory was already presented to you. In the exercises here, it's not really a good case to show off the capabilities of shared memory, because we can use shared memory for a variety of things, like, for example, sharing data, reducing register usage. When we use many registers, let's say, okay, a bunch of data is going to go to shared memory. But in our case, it's just going to be a manually managed cache. And that's actually a fairly close approximation to what happens in reality, because shared memory is basically L1 cache that is programmable. So sometimes the cache does a better job than the programmer, and sometimes the programmer can do a better job than the automated cache. And here's going to be a small example of that. You'll see that the speedup is not huge, but there is a speedup. And one thing to note, which is fairly important about shared memory, is the concept of banks. So shared memory is organized in what we call banks. So each column here is going to represent a bank. And if you want to access something that's you can do one access per bank per cycle. So if two threads want to read from the same bank, well, this is going to serials. It's going to be one thread, then the other. It's the same if two threads want to write to the same bank, even if it's not the memory location. If this thread wants to write here, but this one wants to write there, it's the same bank. So they can't do that at the same time. So it's going to be serialized. It's going to be a bit slower. And when that happens, this is called a bank conflict. And in order to avoid that, it's basically the same as with Coalescent accesses. You want consecutive threads to access consecutive shared locations, because consecutive shared locations are in different banks. Okay? I think that's all I have to say about shared memory. It's a useful tool. The exercise doesn't do it justice. I'm sorry. Okay, now we are going to get to the really juicy stuff. Remember that first we started with an array of structs. So this kind of memory access. So that was element 1, element 2, element 3. So data 1, 2, 3, 4 from element 1, 1, 2, 3, 4 from element 2, etc. We transposed that layout to go to a structure of arrays. So this is going to be data 1 for element 1, 2, 3, 4, etc. Data 2, data 3, data 4. But while doing so, sure, we gained a bit of performance because the test case was flawed. But we also lost the locality, which is a bit sad because we could gain a lot from locality. So the question becomes, how do we gain back this locality while keeping the coalescent nature of the access? And the thing is that a coalescent access just means that 32 threads should access 32 consecutive memory locations. If it's more than 32, so let's say 128, you are not going to gain anything compared to if you just did a group of 32 threads, because the 32 next threads are going to be on a completely different cache line. So there is no gain here. So the ideal memory layout on GPUs is often what we call an array of struct of array, where first you store the data for, let's say, the first 32 elements, or 32 threads, then for the next 32 threads, etc. And inside of each of these blocks, the idea is to store data 0 for all of these 32 threads, data 1 for all of these 32 threads, data 2 for all of these 32 threads. This complicates the memory access And it's not trivial to do. I really encourage you to try to see how you can do that from the code. And if not, you can obviously see the solution. But it's a good exercise. And this is really, I mean, the be-all and end-all of memory layouts on GPUs, especially when locality is important. If locality does not matter for some reason or another, well, you don't care. And Coalescent is good. And finally, let's end on a good note. Is there a way to gain some free performance sometimes? And the answer is yes, sometimes. For some reason, when you use fast math, so first it's dangerous. Do you know what fast math is in general, or should I? Okay. The idea of fast math is to tell the compiler, okay, so my math is going to be normal, so there's going to be no infinity, no nonce, no denormals, which are numbers that are so small so that you don't have the full precision on them. What else? So since you assume that there are no nonce, while typically when you do none equals none, it's false. Here, if you do x equals x, it's going to be optimized to true even if x is 9. So you lose some kind of logic, and also it's going to use approximations. So typically when you have a times b plus c or something like that, things are not commutative because you have machine error, and sometimes you want to compensate for that. So you write things in a precise order. When you tell the compiler, hey, do fast math, he doesn't care. It can reorganize things so that mathematically it's still correct. But numerically, there are going to be differences. And also, it can do fast but kind of inaccurate approximation of transcendental functions like square root, logarithms, and things like that, power, sine, cosine. And these are generally fairly accurate, but you can lose a few digits of accuracy. And I mean, if your application is okay with it, then that's great. If not, well, perhaps you can't use that. So that's always something that's worth trying. Extra device vectorization also happened to improve my performance in some test cases, but fairly rare, just another compile flag for NVIDIA. And then we have launch bounds. Launch bounds is something that you put above the kernel, and it tells the compiler, hey, I make a promise, I'm not gonna launch the kernel with a block size larger than what you put in the parentheses here. And typically that allows the compiler to do more optimizations, like managing the resources, knowing that you don't have more than some number of threads, allows you to better utilize the caches and the registers most of the time. Because sometimes you don't tell him anything, then you tell him, okay, I'm not gonna use more than block size threads. And the performance is worse because compilers are horrible and it's immensely complicated. So that's gonna be my last slide. You can't really assume that any of what's presented here works and makes sense. Here's what kind of caused a small depression in my PhD. I had this code, and I mean, the one here is because it's a template argument that was always one anyway. If I did that, I mean, try r is greater than 0, obviously, because we are inside of the if statement. So this could be optimized that, okay, prism r is just, I mean, this. Nothing crazy. When I replaced these two lines by these two lines, the code became 1.3 times faster overall, so the kernel became 1.5 times faster. It makes no sense. It makes no sense. It's maddening because how would you ever find that? I don't know.
Actually, you're doing an if statement in the
I'm doing an if statement here.
Oh, in the
You mean, yes, it does the if statement, but it does not do the kind of if statement here, this one. So the if statement is the same, so it should not change anything.
No, when you define your int, inside the int, you do an int with the question mark.
Yes.
You do an if.
Yes.
You do two ifs
Yes.
So that's why it's lower.
No. No. Because the cost of an if is basically free. Ifs are slow if different threads are either true or false, which is called branch divergence. It was not the case here. And on top of that, it's something that the compiler should optimize out because you have the guarantee that try R is going to be positive. Perhaps, I don't know. And also, it's not possible that you spend 30% of the time on just that. So occupancy is perhaps the only logical explanation. But yeah, I don't know. I also have similarly to that, at some point I added a big piece of code and there was a template argument in the kernel so that you can either activate or deactivate this piece of code. And when you activate the piece of code but never reach it, so it's more code on the GPU, so more registers, etc. It's bigger, should be slower. The occupancy should be slower. It was faster, and by like a factor of 2. I don't know. So take away from this, do measure, do the benchmark, and if it makes sense and your performance is better, that's great. If it does not make sense, but your performance is better, that's also great, but you have to live with it and live to perhaps understand it one day. Yeah? The assembly? Yes.
Because if you perhaps it's a matter of allocating your resources in Microsoft for but that's actually
yes, it's probably something like that. It's probably something like that. And you can actually do that, look at that in the inside profiler, the NCU profiler. When you go to the tab source, and then you select source, you can see on the left your source and on the right a bunch of different metrics like what kind of access is done, the number of live registers, so how many registers are used at this point in time, etc.
Yeah, but you can detect the registers or memory that are not used or very not used, not used by the user.
Oh, you mean could the optimizer do that?
Yeah, I think some stats on how often you access some allocated something.
I don't know.
In this situation, imagine you allocate a register for the -1 but you never have 6 places. So you would have it access once to initialize it, then you run your code, but
so it's just a register wasted. That's what you mean?
Yeah. So is it simple that you tell you, okay, that one is probably good for restart because you never use it?
As far as I'm aware, no, but I may be wrong there. So I think what you're suggesting is kind of how is it called?
Like the kind of one that and you just declare variable, but you never use it. Okay, you probably don't need that because you never use it.
Okay. The compiler tells you that, but in this case, it didn't tell it. Yeah. And the case is tricky. I agree with that. And but the result was surprising. The amount of performance gain there was surprising.
Is it possible the condition evaluating because of the or1? The or1 is always true.
Yes.
So perhaps it's not even perhaps it's optimized by removing the first condition. Try error about 0 can be removed because
yeah. I think it's something like that. But then again, in this case, it's also the case.
Yeah, in this case, probably the is always true.
Yes.
Yeah, I mean, the try are above 0 is not essentially true. In fact, it may not be true. Well, I don't know.
Oh, yeah, I see what you mean. Yeah, you're right. Yeah, you're right. Anyway. point is, there are some things that are tricky and not obvious, and their impact is not obvious. So yeah, that's the conclusion. But you're right that this probably explains why it triggers something that's big at this point, and why it couldn't be optimized. And then the consequence is just bad luck, because it probably came at a point where we are into step into occupancy. Any questions? If not, we still have a few exercises left. And yeah, no, that's the end of my slides. We have 30 minutes left, so no, I think it should be enough. The setup is done. C'est laquelle? C'est... Non, c'est dans mail.cu. C'est Expert Fusion. So the changes here are in the CU file, not in the H file for the 6th exercise. Yeah.
The flag additional visualization, the additional flag
Right.
additional visualization, you want that?
No. Item? Yeah. No, no, no. I knew that was pretty well everything. Remember you from view in my preferences, so I'm just looking at now what kind of program how it works in the production too. So yeah, I'm interested in how to use the whole thing like free well that free repairs and everything. Might not like use libraries or something like that. But yeah, if we link them then that Kernel. That's a yeah, I guess also good
We think the five. To be fair, I've never really used IGAM. I mean, I know it exists. I've used it in one project very quickly at some point. I use it in I use it once for presenting my facility. And worked really well. Pretty nice students. They wanted something that was really what from the command part. They want to bring different instead, and that's very important. Yeah. What's important to do especially. How does it manage memory? I mean, memory allocation. In the order. No, do you give it the pointer that you malloc yourself, or can you? Okay, you can either set it so you can provide you with pointers which actually yep. Or you can just I guess you can give him a raw allocator if you want to. You can. That's nice. And again, all this discussion, Coalescent versus locality, is basically the same as for context. Yeah, that's pretty easy. Yeah. Yeah, that's tricky. Do you want a hint / a comment on doing the kernel version, or is it okay and can we move on? Or do you want more time? I don't know. Should I give a comment now, or wait a bit? No? Okay. I'm gonna wait a minute or two. Salut. Okay, quick comments about this change. This is the statement for the next problem, so don't pay attention about this. The idea that was that we had the DUDT, then we had an XPy, which basically took the result of the DUDT, so the right-hand side, and added it to some base vector to produce a solution. So that's what I mirrored here. The right-hand side, I'm computing it, so it's not an argument. And I add that to some base vector, and I write the result in some out vector, okay? And also there is a coefficient for the right-hand side, which is basically delta t. What's this? No. This is a mistake.
So when writing the data back, I could just do this, because this saying out equals space plus the coefficient times the right hand side, which I computed. So that's always true. And here I added a small optimization saying that, okay, if the base vector on which I add stuff is also the solution vector, which I already have loaded, I use the solution that is in the registers instead of the solution that's likely in the cache, because this one is going to be a little bit faster. Whereas this one is going to read it again, and even if it's in the cache, it may be a bit slower. So that's the complete extent of what was what needed to be done. And how well does it perform? Well, when you look at the kernels individually, you see, okay, that's great. We went from 290 microseconds, and we landed on, wait, 368 microseconds? No, that's wrong. No, it's not wrong. Because now these kernels, they do more work, but there are fewer kernels. We don't do the XPy, so overall it's faster. This, it's really easy to do, and it can be very effective because overall, here we went from 600 microseconds to 550 microseconds on the overall temporal scheme. In what we did in real life, it was closer to a third faster. So it can be useful. And that's it. Also, a small comment for the next exercise. Come on, where's my mouse? Things have been pre-baked in some sense. So the idea is to use shared memory for 3 components: X, Y, and what we call the bathymetry, which is the depth of the water, because this is use the shallow water equations. So you can just activate this line to index into this array, which is local. You will need a local index, hence this local index. And that's basically how you write into it. So you write field node, and instead of using IE, which is in general the index of the triangle, you use IE local, which is your local index. And so everywhere where you have a hint, that's where it has to be changed. And instead of IE, you use the IE lock. And that's basically it. Boom. Here too, instead of data, you can use and triangle left to use the IE lock. Not here, because this is the right one. Here you can use it too. And here and here as well. And that's it. We don't have much time left, so if you don't have time to do all of this, it's okay.
Is there a way to get kernel fusion done automatically? Maybe not using C code like this, but I know some higher level stuff lets you try at least to automatically. So
I think even the CUDA compiler can do a bit of that if the kernels are on the same file and launched in that file, because I mean that's what you said.
No, that's inside the kernel. There was some code that was not together with the line in the
Oh, okay. So that's not that's it.
But I mean, I guess in principle, the compiler can do it so that you can compile it. Also, maybe the compile flash. It's quite, it can also be done with the compiler flag development.
But regarding libraries like things, what's it called? Perhaps JAX can do something like that. I don't know. Yeah, probably. I haven't much experience with them. Vous en êtes où en termes de trucs? Le 6, c'est fait? Le 7? Non. Oui, on est dans le 7. Qui a fini le 7? Qui a fini le 6? Ouais.
Qui a décroché?
You are so fast, you can keep the number that
For the 6? It's because I avoid writing and then reloading the same data to global memory. Hmm? No, never. Yeah, from the registers to global memory. I avoid that copy. Since it seems that everyone is kind of going, I suggest that, I mean, I want to give a quick word about the ninth optimization, no, the 8th optimization with which is the array of struct of array. And then I think we can close I mean, you can finish for today. Where is it? Here it is. Okay. Quick word about this. So the idea here is to have both locality, so that if the element increases, so the element number, this is the last index, we are basically moving alongside the memory. So element 0 is going to be at the left of the memory, speaking, figuratively speaking, and element 10 million is going to be much further away. But we also want consecutive threads to access consecutive memory locations. So how we do that? How do we do that? Well, the idea is to divide the whole buffer into different blocks. So first block for the first 32 threads, second block for the next 32 threads, etc. So that's what those two things do. The block is which block am I? So if I'm from 0 to 32, it's block 0. From 32 to 64 is block 1, etc. And what is my local index inside of this block? Okay. And then the way we can access data is that I move the block times the size of my block. And what's the size of my block? Where it is three-dimensional, one dimension is 3, one dimension is unfilled. And the third dimension used to be the number of elements, but for blocks is the size of the block, which is called AOSOA here. And then I have to access the data inside of the block in the same way as I did with a coalescent access. And so you'll notice that the only thing that changes compared to the previous version here is that instead of using NLM, I'm using the AOSOA value, which replaces the NLM because it's the size of my block, whereas previously it was the number of elements. And instead of having the element as the last index, I have the remainder here. But it's okay, because if the element increases by 1, the remainder also increases by 1 most of the time. So this is still going to be coalescent, because this has the size of a cache line, but it's also fairly local, and this is kind of a good way to do stuff. And with that, we went from 540 microseconds to 440 microseconds, I think. So it's almost 20%, I think. Yeah, that's right. And yeah, that's all I wanted to say about that. And finally, when we do when we add the compiler flags, it depends on the GPU. On my GPU, it did absolutely nothing. On Lucia, it's massive. I don't remember the value, but the value was 389 microseconds compared to 440. So another 50 or so microseconds, Yeah. So again, fairly significant at basically no price, except for a bit of accuracy here and there. So yeah, that's it for today. Hopefully this gives you some idea of what you can potentially do. And as always, try it, measure it. If it works, it's great. If it doesn't work, well, at least you tried it. Thank you. Also, if you want to learn what to do, use the Insight profiler and read what's written on it. It's a gold mine.
Lisez les messages.
Lisez les messages. Ouais. Ce truc-là.